Let us look at an application of the Nyquist criterion for checking the stability of a system. As I said earlier, the Nyquist criterion is useful mainly because in cases where the model for the system is not known, but it is believed that the system has a linear time invariant model of the kind that we have been looking at, described by a nth order linear differential equation with constant coefficients, etc. An experimental measurement of the gain corresponding to the loop transfer function can be used to determine stability. If you recall, this loop transfer function was GH, and instead of S we put j omega, then this is a complex number GH of j omega, and its modulus gives you the gain, that is the ratio of the output amplitude to the input amplitude in the steady state when the input is a sinusoidal signal of frequency omega. Now, this is something which can be experimentally determined. You apply an input and then measure the output. Now, where do you apply the input and where do you measure the output? Let me repeat. Here is this gain k, and here is this feedback transfer function h, the forward transfer function g, the difference device, etc. We open the system here and then apply the input at this point to this input of the amplifier k. So, the signal then is amplified, passes through the transfer function of the system g, and then passes also on to the transfer function h, and then you measure the signal at this point. So, the ratio of the Laplace transform of the signal here to the Laplace transform of the signal here is exactly gh k gh of s. And if the signal is sinusoidal, then what we are discussing right now will hold, namely I may put the k here also. If I look at the modulus of k gh at j omega, then that will be the ratio of the amplitude of the sinusoidal signal here divided by the amplitude of the sinusoidal signal here. In practical terms also, this means something. For example, think of our motor control example. What you are going to do is you are going to apply a sinusoidal input voltage to the amplifier, which then results in a amplified voltage which is applied to the motor. The motor will run, and the motor shaft has the tacho generator on it. So, the tacho generator will also produce an output. The only thing is, in normal operation, the input here is a DC voltage. It may be changing, but it is unidirectional. The output of the tacho generator voltage is also going to be a DC voltage. But under test conditions, you are applying an AC voltage, maybe of a small amplitude here, and measuring an AC voltage of another amplitude here. So, this test can be actually experimentally performed. Of course, in all of this we are assuming that the load torque is either 0, or when doing the theoretical calculations we are only looking at the effect of the input, the reference input, on the performance. So, here in this case, for example, the motor will not be loaded, it will be run under no load conditions. Of course, it will not run at the rated speed and all that. Similarly, the argument of this complex number gh j omega or k gh j omega is equal to the phase difference or the phase shift from the input at this point to the output at this point, and this is something which also can be measured experimentally. So, in other words, you know the modulus and you know the argument or the angle corresponding to this complex number k gh j omega. So, all you have to do is, from these measurements you can plot this complex number in the complex plane. So, this plot is known as the polar plot. And why polar plot? Because the modulus of a complex number and the argument of a complex number, these correspond to the polar coordinates of a point in the complex plane. But it is also known as a Nyquist plot, because Nyquist showed us how to make use of this experimental information. Now, a polar plot may look like the following. At the moment you may not be able to guess what kind of a system will it be for which the polar plot will be as shown, but let me draw a typical polar plot. So, let us say it starts from a point here and then it goes like this towards the origin. Now, let us remember one thing, when you do an experiment, you apply a sinusoidal signal of angular frequency omega. Of course, omega is 2 pi f, where f is the frequency in hertz or cycles per second. Now, obviously, when you do an experiment, you can only choose a number of different values of the input frequency, say starting from omega equal to as low as 0.1 hertz, maybe 1 hertz, 10 hertz, 100, 1000, 10,000, or maybe a few more points in between. So, in other words, the data that you are going to get will only consist of a number of points like this. And the angular frequency omega, of course, being 2 pi f, is necessarily only a positive number. So, here omega is only positive. Omega equal to 0 corresponds to DC, but DC is not AC. So, in fact, all of this does not hold for DC, although you can do an experiment for the DC case also, that is, apply a voltage, DC voltage at the input and measure the tacho generator output voltage. So, one can do a DC test also in this case and we will get this number corresponding to, say, omega equal to 0. And then you go on increasing omega, all you get is a number of points like this, and then as we do for any experimental data, we join these points by as smooth a curve as possible. So, this will be the kind of curve that will result. And as is obvious, you can only apply frequencies up to a certain upper limit. If a frequency is too high for the case of a system like a motor, it will not just make any sense, the motor will hardly turn if the frequency is very high because of its inertia, the inertia of two kinds. So, there will be an upper limit on omega, maybe omega will be up to 10 kilohertz. So, in other words, this response will stop somewhere, the measurement points will end up somewhere here, and one is now extrapolating to go beyond that, trying to sort of guess what will happen when the frequency is increased indefinitely. So, remember that the polar plot may actually start under DC conditions, but it never practically is going to correspond to the situation which can be indicated as a limit as omega tends to infinity. This limit we have to guess. How far we can guess it depends on the system. Is 10 kilohertz sufficiently high, or do we have to go further up? From the trend of the data, one can see what is likely to happen. So, let us say here we have chosen some number of values of omega, and this is the kind of plot that we are going to get. Now, this is a plot of kgh j omega, and if you remember, if you go back to the Nyquist contour, the Nyquist contour consists of a part of the j omega axis closed by what I called, or what I drew like a semicircle in the right half of the complex plane. And in other words, this part corresponds to minus j omega to plus j omega, and then there is a circle of radius, say, omega, and the argument changes from pi by 2 to minus pi by 2 in the clockwise sense. So, this was the whole Nyquist contour. What we are doing now is we are only looking at this part of it corresponding to the upper half of the j omega axis. The data that we get for the polar plot from the experiment corresponds essentially to a number of frequency values or omega values or j omega values on the j omega axis. So, this is the polar plot. Now, as I told you, the transfer function usually has only real coefficients, and therefore, gh j omega will be the polar plot, the image of the Nyquist contour will be symmetric. The Nyquist contour is symmetric around the real axis, and therefore, the image contour will be symmetric around the real axis. And because of that, if I know that the polar plot for positive omega, that is for values of j omega which lie on the upper half of the j omega axis, looks like this, then the values for omega negative, or in other words for points lying on the lower half of the j omega axis, will be the mirror image of this in the real axis, and so it will look like this. Experimentally, we only determine this part, but we immediately infer that the part corresponding to the lower half of the j omega axis will look like this. and of course it goes through this point omega equal to 0 or j omega equal to j 0. But what about omega tending to infinity? Well, this upper part corresponds to omega tending to infinity, so the lower part will then correspond to omega tending to minus infinity, or in other words, one end of it corresponds to this point on the Nyquist contour, the other end of it corresponds to this point on the Nyquist contour. But these 2 points are not the same point, they are separated, although one of them is j omega with omega very large, say 10 raised to 5, the other is minus j omega with omega very large, the same value, minus j 10 raised to 5, but this is not quite the same thing as j infinity and minus j infinity. And as I told you, the contour has to be closed, and therefore it is this part of the contour which also we have to consider. Experiment tells you what happens on this part. By symmetry we know what is happening on this part, but what is happening on this part? Now this is something we have to figure out from some knowledge about the system, as we will see. So the Nyquist or the polar plot experimentally will consist of this half of the almost a full figure, except for this transition from j omega, omega large positive, to minus j omega through the right half plane of the z plane along that semicircle. Now let me remind you once again about the principle behind the Nyquist criterion and the role that the point minus 1 plus j 0 played in the whole thing. If you remember, we were looking at the rational function 1 plus gh or 1 plus kgh, whose numerator was the characteristic polynomial, and our main interest is in the roots of the characteristic polynomial, whether there are any roots in the right half plane. The denominator of it is gd hd, the denominator polynomials of g and h respectively, in other words the poles of the forward transfer function g and the feedback transfer function h. So it is 1 plus kgh that we are looking at, and we applied the principle, Cauchy's principle of the argument to 1 plus kgh. But we observed that the plot of 1 plus kgh is going to differ from the plot of kgh by only the addition of this 1. Similarly, the plot of kgh will differ from the plot of gh by the multiplication or scaling by the factor k. And so it is enough to consider the plot of gh or under the action of gh rather than under the action of 1 plus kgh. Now in the principle of the argument, this whole 1 plus kgh, we want to find out whether it encircles the origin and what number of times, and in the same sense or in the opposite sense as the original contour. Now what is the relationship between the plots of 1 plus kgh and gh? For the sake of simplicity, let me show, let us say the plot of gh turns out to be a small circle like this. This is the plot of gh, that is whatever is the contour in the z plane, the image contour, let us suppose, looks just like this, a small circle here. This is the plot of gh. What will be the plot of kgh? Kgh is a scaled version of this by the factor k. So let us say if k equal to 2, then what is going to happen? Each one of these points is going to be multiplied by 2. So in particular, this circle will be such that its center will now be at this point, and this circle will have double the radius. So this will be the plot of 2gh. If the plot of gh is like this, the plot of 2gh will be like this. It will be scaled, all the radius vectors from the origin will be doubled in length. So it will be a circle of double the size, in the sense double the radius, and the center has shifted to a place which is 2 times as far from the origin. So this is the plot of 2gh. Now what about the plot of 1 plus 2gh? So I have to add 1 to it. So I am going to shift this circle now by 1 unit. Let us say 1 unit on this scale is such that this plot looks like this. So this will be the plot of 1 plus 2gh. So this was the plot of gh, this is the plot of 2gh, and this is the plot of 1 plus 2gh. Now you are looking at the relationship between this plot and the origin. Cauchy's principle of the argument tells you that the image contour, the number of times it encircles the origin, is related to something else. So we are interested in the encirclements by this of this point. But now you can see the relationship between this point and this is the same as the relationship of this 2GH contour with the point minus 1 plus J0, because this is 1 plus 2GH. Therefore, the relationship between this plot and this origin is the same as the relationship between this plot and the point minus 1 plus J0. That is the origin, instead of the origin we move 1 unit to the left. So, the number of encirclements by 1 plus 2GH of the origin will be exactly the number of encirclements by 2GH of the point minus 1 plus J0. And so, instead of talking about encirclements of the origin, which is what is involved in the principle of the argument, in the Nyquist method we talk about encirclements by the plot of KGH of the point minus 1 plus J0, and this is the reason for the special role that this point minus 1 plus J0 plays. And of course, as I told you that we really do not vary the gain in practice. So, we have to find out the effect of the gain by simply considering scaling, and we will see how this will affect our calculations. So, remember this is why we have to look at encirclements of the point minus 1 plus J0 by the polar plot. Now, going back to the example that I had drawn earlier, we are now to think of the rest of the original contour, that is, here is this contour once again. What about the image of this part of the contour? Now, about this cannot be experimentally determined, because the frequency response method applies only to this part of the contour. This part of the contour cannot be experimentally determined, but if we have some knowledge about the system, and this of course we do, we are not just looking at a system about which we know nothing. For example, we know that in the case of the motor there is a first order transfer function for the armature circuit, another first order transfer function for the mechanical part, etc. If we use an integrator, we know that there is one more first order transfer function 1 by S, and all of this we know. So, because of this we can find out something that happens along this part of the contour. Now, on this part of the contour I can say that the complex number S is given by what? In polar form, r e raised to j theta, where r is the radius of the circle, semicircle, and theta is the angle or the argument of a point on it. Here is r. Of course, I had called this omega. So, instead of r you can think of omega. So, the complex number S along this semicircle is simply omega e raised to j theta. And now, what am I doing? I am just evaluating GSHS, that is GH at S or K times GH at S for any complex number S on the contour. For the point on the contour corresponding to that semicircle, S is r e raised to j theta. Therefore, this is going to be K GH r e raised to j theta. Now, this is where we make use of the fact that this r is going to be a large number, and we will come to understand what is meant by large and why. Now, if you recall our root locus method, there we were, one of the rules that Evans had given was the following: to find out whether a point in the complex plane lies on the root locus, you have to apply the angle criterion. That is, you have to measure or draw lines and measure the angles made by that point at the poles and zeros of the transfer function GHHS. And then, if that point was on the polar plot, to determine the gain corresponding to it, you had to determine the distances. And if you remember, at that time we drew vectors from the poles and zeros to a point in the complex plane. Now, you can imagine that exactly the same thing is done here for trying to find out what is going to happen to this KGH of S along the semicircle when the radius of the semicircle r is quite large. So, to do that, let us do what we did earlier. We look at the pole 0 plot of the transfer function, and let us say the pole 0 plot looks like this. I am just showing some poles and some zeros. I do not have any specific system in mind. There could be poles in the complex plane, there could be zeros which are not real, but on the complex, all that is okay. Now, here is this point S, and this point S is at a distance r from the origin, and this r is going to be considered very large. Then GH of S, as we saw earlier, looks like a product of linear factors in the numerator divided by a product of linear factors in the denominator. And what are those factors? Essentially they correspond to the poles and zeros. So for example, here is a 0 here, let us call this point Z1, then there is this factor S minus Z1 corresponding to it. But what is the vector S minus Z1? The vector S minus Z1 is very well represented by this line drawn from Z1 to S. There is this other 0 Z2, so I can draw the vector or the line from Z2 to S. So this represents S minus Z1, this represents S minus Z2. Similarly, there are poles, let us say P1, P2, P3. In the denominator, I have factors S minus P1 corresponding to this line, S minus P2 corresponding to this line, and S minus P3 corresponding to this line. So what do I have then? I have product of the two vectors corresponding to the zeros divided by the product of the three vectors corresponding to the poles. And remember, now we are considering this radius to be very large. Now because of that, if you look at the length of the vectors is also going to be very large. In fact, it is going to be very nearly equal to the radius r. On this diagram it does not appear to be so, because I have not chosen r sufficiently large in comparison with the magnitudes of the poles and zeros. The poles and zeros are all here. I have shown a point S which is not really very far away from the origin. But imagine that the point S was at a distance which was 10,000 times any one of these distances, then all these distances would be nearly equal to r. And therefore, what will I have if I look at the magnitude or the amplitude of GH of S? It is going to be what? Roughly corresponding to this factor r, corresponding to this other 0, another r, so r square in the numerator divided by r for each one of the poles, and therefore r cube in the denominator, and therefore it is going to be roughly like 1 by r, and if r is very large, then it is going to be nearly 0. Essentially what I am saying is that the modulus of GHS for S equal to r e raised to g theta, when r is sufficiently large, and now what do I mean by sufficiently large? R is much larger compared with the distances of the poles and zeros from the origin. Now for the given motor, for example, or some other system, we may have some idea about the poles and zeros. In fact, we can make measurements of the various parameters of the system and in fact determine the various poles and zeros. But even if we do not know them exactly, we may still have some idea as to how large they might be. And we are only considering, we are not doing any actual experimentation, we are only considering theoretically points S which are sufficiently away. So in that sense, we can always say that by choosing r sufficiently large, this is what is going to happen. The whole modulus is going to be nearly equal to 0. Now why is it nearly equal to 0? Because in the numerator I have r square, in the denominator I have r cube. Now where does this r square come from? This comes from the two zeros, and the r cube, it comes from the three poles. So what is happening here? The number of zeros here is less than the number of poles, or the system has more poles than zeros, and because of this, along that semicircle, when r can be considered very large, modulus of GH of S will be nearly 0. And because the modulus is nearly 0, the argument is not really going to matter that much. And therefore, when I look at the image of that part of the contour, the semicircle, under the action of GH, it is going to be some curve here very close to the origin. It is not going to be a closed curve as I have shown here, it is not a circle or anything, I do not know what its shape is, but it is going to be so small that it can be considered to be virtually at the origin. And therefore, in our experimental figure, if this was the polar plot coming down to high frequencies, this was the mirror image of it. So this corresponded to the j omega axis part. The semicircle image will be something which is very close to the origin, so some curve joining the two ends of it here. So this is what we can conclude, because this is what will happen if the number of zeros is less than the number of poles, and this is the case in practice. In most practical systems, the system has more poles than zeros. If the number of zeros is equal to the number of poles, then the situation is going to be different, because then in the numerator and denominator I will have equal powers of r. As a result, the ratio will not go to 0 as r goes to infinity. and should it happen that the number of zeros is greater than the number of poles, then it is going to be of course drastically different, because now the numerator has a higher power of r than the denominator. So, the modulus is actually going to go to infinity instead of going to 0. Let us not look at these two cases. Once you have understood what is happening, it is not very difficult if one comes across a practical example or even to study it in theory, these two cases z equal to p and z greater than p. So, we will not look at those cases, we will only look at the case z less than p. Now, with that then, from experiment I can determine this upper part, what looks like the upper part here. I take the mirror image in the real axis, so I get this figure, and because the image of the semicircle is virtually something, a curve which is very close to the origin, I can show it like this actually by joining these two and going to the origin. Although in practice, if I write here j infinity, I do not really mean that I apply a signal of infinite frequency and I make any measurement. That is all nonsense. There is no signal of infinite frequency that I can ever apply, but I can apply a signal of whatever high frequency is under my choice, whatever signal generator which will provide some power to drive the motor. In the case of the motor, it may not really be of the order of megahertz or even kilohertz, it may be of the order of a few hundred hertz. Still, that may be adequate because the image or the frequency response will be such that it is virtually very small. So, this is what we mean here. Now, therefore, this is the contour gamma prime, which is the image of our original contour gamma. And now we are ready to apply the Nyquist criterion to this plot. Now, remember, we have to consider the encirclements by this plot of the point, of which point, not the origin, but of the point minus 1 plus j 0. Now, for high frequencies I am very close to the origin, so the point minus 1 plus j 0 might be somewhere here, let us say. Now, it is clear from this figure that this plot, that is gamma prime, does not encircle this point minus 1 plus j 0. Now, this is for some particular value of k, because experimentally I may have chosen some value of k. Now, what if I increase k? What if I decrease k? Now, again, as engineers we ought to be able to visualize what is going to happen. If I increase k, then what is going to happen is this plot is going to blow up, so to speak. That is, it is going to be upscaled by that factor k. As a result, everywhere the values will increase, they will be multiplied by some positive number. So, this point instead of here will start here, and the new curve may look like this. Similarly, its mirror image will be enhanced in size and it will look like this. But will it encircle the point minus 1 plus j 0? No, it does not look like that. Even if I increase k by 100 times, one can now see that the new plot, the new gamma prime corresponding to that new value of k, will still not encircle the point minus 1 plus j 0. On the other hand, if I consider values of k which are smaller, then the scale is getting reduced, then it is even easier to see that the new plot or the plot corresponding to that value of k will not encircle the point minus 1 plus j 0. For example, if I reduce it by a factor of 2, then this plot will become 1/2 in size and will look like this, and this certainly is not encircling the point minus 1 plus j 0. So, this is how, with the experimental Nyquist plot, completing it this way by using this fact that there is this mirror image business. Also, if the number of poles is greater than the number of zeros, then this is what is going to be the image of the infinite semicircle. We can look at the relationship of the plot with respect to the point minus 1 plus j 0 and determine the number of encirclements of this point by this plot, and that corresponds to what? That by Cauchy's theorem equal to the number of zeros of 1 plus gh divided by the number of poles of 1 plus gh, and that enables us to determine the number of zeros of 1 plus gh in the right half plane, because according to that the number of encirclements therefore is equal to the number of zeros of 1 plus kgh minus the number of poles of 1 plus kgh. But as we saw earlier, 1 plus kgh essentially is the characteristic polynomial divided by GD HD, the pole part of G and H. So, this number of zeros of 1 plus kgh is exactly equal to the number of roots of the characteristic polynomial in that contour gamma, the Nyquist contour gamma, and minus the number of poles of 1 plus kgh is exactly the number of poles of GD HD inside the Nyquist contour. So, the number of encirclements is equal to the number of roots of the characteristic polynomial in the right half plane, actually not in the right half plane, in that contour gamma, inside that contour gamma, minus the number of poles of GH inside the contour gamma. Now, suppose we know, and as I said, we have to know something about the system, otherwise we really can't do much. We know that the GH transfer function has no poles in the right half plane. In that case, this number is 0. Now, if the number of encirclements is also 0, then you have 0 equal to the number of roots of the characteristic polynomial minus 0. Therefore, the number of roots of the characteristic polynomial inside the Nyquist contour gamma is going to be equal to 0. In other words, the characteristic polynomial has no roots inside the right half plane, and therefore, the closed loop feedback control system is stable. Not only that, it is stable for all values of k, positive values of k, because no matter what positive value of k we choose, the number of encirclements is just going to be 0 for all those values. Therefore, for all those values of k, the characteristic polynomial will not have any root in the right half plane, and therefore, for all those values of k, the closed loop system will be stable. Now, the plot I drew to illustrate the application of the Nyquist criterion is almost the one that corresponds to our motor control problem with the proportional feedback. Maybe some of you have been able to see the relationship. Of course, there is going to be a slight difference between the two, as you will see. Now, if you recall the analysis that we did for the motor control system, the feedback transfer function H, what was it? It was essentially nothing but the tacho generator gain, KTG, because the feedback element was simply the tacho generator, and this was the gain from the input speed to the output voltage produced by the tacho generator. So, H is not really a function of S, or S does not appear there, it is just a constant function of S. What about the function G of S? If you remember, there were two parts to this G of S. One was the relationship between the armature voltage and the motor current, or it depended on that, and the second was the relationship between the motor current, which determined the motor torque and the speed. So, there were these two parts of that transfer function, and as a result, that transfer function G of S had a denominator which was a quadratic, and I had written it earlier as something like S squared plus AS plus B, and then it had some term in the numerator. So, GS was a transfer function like this, or in other words, it was a transfer function of second order, and therefore, if you look at GH, then there are two poles, and as far as the armature voltage is concerned, or the relationship between the reference voltage or the armature voltage and the speed is concerned, the numerator is just a constant, and so this GH has only two poles and no 0. Now, because of this, what is the polar plot going to look like? So, let us factorize this S squared plus AS plus B into the two poles. Therefore, GH of S is going to be essentially some constant number in the numerator divided by S minus P1 into S minus P2, where P1 and P2 are the two poles. Now, these two poles, as we had seen earlier, are in the left half of the plane, and they may both be real or they may be complex. So, let us consider the situation when the poles are real. So, here is P1 and here is P2, and I have to look at GHS corresponding to this P1 and P2 for what points S. Now, for the part of the contour which is on the j omega axis, I have to consider points S here. Now, this is what corresponds to the experimental data. So, here is a typical point j omega. Now, what about GH of j omega? Now, once again, it is not necessary to substitute any numbers and compute it to find out what is going to be the nature of GH of j omega. Once again, we draw the vector from the pole to the point j omega, from the other pole to the point j omega, and what we have is then GH of j omega will be the complex number, which will be some number in the numerator divided by the product of two complex numbers in the denominator. What are these two complex numbers? They are the complex numbers corresponding to these two vectors drawn from the poles to the j omega point. Now, it is easy to see that the argument of this complex number g j omega is going to be what? What is the argument corresponding to this factor, that is j omega minus p1? It is the angle made by this vector with the positive real axis. So, it is an angle that lies between 0 and 90 degrees, perhaps it looks here something like say 60 degrees. What about this angle? It is also an angle made with the positive real axis, it is a positive angle maybe of the order of 30 degrees. However, these two factors are in the denominator, and therefore, as far as the argument of GH is concerned, j omega, it is not going to be a positive angle, but it is going to be a negative angle, and it is going to be a negative angle lying between 0 and 180 degrees. And as a result, when I do the experimental plotting, what I am going to get is not going to look like what I drew earlier, but it is more likely going to look like this. Now, this corresponds to the DC case, and therefore, this is referred to as the DC gain of the motor. And then as you apply AC and increase the frequency, we will get points along this part. So, the plot corresponding to the positive or the upper half of the j omega axis is really going to be this, and this is what will be obtained experimentally, and the other part will be inferred because of symmetry. And of course, I will show them both as actually passing through the origin, although in practice they will not come to the origin because of the argument earlier, that in this case the number of poles is 2, the number of zeros is 1, therefore, the image of the semicircular part of the Nyquist contour will be essentially very close to the origin. So, will be a point like this. So, except for this interchange, when I drew the figure first, I do the upper half, and then I said that the lower half is the mirror image, whereas experimentally for the motor you will get this part and the upper half will be the mirror image. The total shape remains the same, and the total conclusion therefore remains the same, that the closed loop system consisting of tachogenerator feedback, that is proportional feedback, no matter what the gain k which is applied at the input to the armature, no matter how large it is, the system will remain stable. Now, when we use the root locus method, we were able to get more information than this, because we were able to find out the location of the closed loop poles, and from that we could find out information about time constants and things like that. Now, that information we cannot obtain here, at least not immediately, although it is possible to, from this polar plot, to conclude something about even time constants, but that is not very easy, that requires a lot of argument, and we will not go through it right now. I will refer to it later on, but you will have to read up your textbook carefully and in detail to get some information about that aspect. But as far as stability is concerned, there is no problem here. So, the feedback control system, proportional feedback control system that we had studied for the motor control problem, motor speed control problem, is going to be stable. Now, that conclusion we had drawn earlier by actually finding out the transfer functions by using the root locus plot. Here now the same conclusion we can reach by looking at the experimental data, namely the Nyquist plot or the polar plot obtained from the experimental data, then completing it this way by using the symmetry of the Nyquist plot, and by using the fact that the number of poles of the system is greater than the number of zeros. Therefore, the encirclement relationship around the point -1 plus j0 is going to be 0, and therefore, from that we concluded that the number of roots of the characteristic polynomial inside the or in the right half plane or inside the Nyquist contour is going to be 0, and therefore, the system is going to be stable. Now, Let us apply this to the integral feedback case. Now, what is going to be the difference with the integral feedback case? Now, the main difference is that in the forward path we have introduced the integrator. So, in place of k now we have k by s as the block that precedes the motor armature. So, after that I have G as before, and then I have H, the tacho generator, as before. There is no change. The rest of the arrangement is exactly the same. Now, what about the stability of the system when I use an integrator, that is when I use proportional and integral feedback, when the gain of the integrator, or that is the proportionality of the integral part of the feedback, is increased. Of course, we had found out earlier using the root locus method that the system was going to become unstable. And how did we conclude that? Because then G has 2 poles, H has no pole, G has no 0, H has no 0, but there is this additional pole at the origin corresponding to the integrator, S. Therefore, the total system now has 3 poles, 1 0. Because of that, there were 3 asymptotes, and therefore 2 asymptotes went off in the right half plane, and therefore for a large enough value of k, the system would become unstable. This was the conclusion that we had drawn using the root locus method. Of course, for what value of k, to determine that, one has to use the Routh-Hurwitz criterion or the Routh criterion or the Routh table. From that we have been able to calculate the value of k. Now, let us look at it from the point of view of the Nyquist criterion or the polar plot. Now, what is going to be the polar plot of the new loop transfer function? G is there as before, H is there as before, I have this factor k by s. Now, it is not necessary for me to repeat an experiment, breaking open the loop here, applying an input here, and then seeing the output here. I have already done the experiment for the GH part. It is not difficult to figure out the effect of the S part, and that is because we are to replace S by j omega. So, if I do that, I will have a 1 by j omega multiplying the original kgh. Now, what is the modulus of this and what is the argument of this? What is the modulus of this? What is the modulus of 1 by j omega? It is 1 by omega. So, when omega is increased, the modulus is going to become small. It is going to become a number approaching 0. But what about the argument of 1 by j omega? Now, I hope you have not forgotten your j manipulations. The argument of 1 by j omega when omega is positive is minus pi by 2 radians or minus 90 degrees, or this integrator produces a 90 degree lagging phase shift. Therefore, the phase shift of the original GH loop transfer function is increased by an amount 90 degrees, and the phase shift, as I had pointed out just now, was a lagging phase shift, as a result of which the lagging phase shift will be increased further by 90 degrees, and therefore, the polar plot or the Nyquist plot or the frequency response data will give you a plot which is going to look like what? At very low frequencies, there is no phase shift difference. So, it will start here as it did, and then it will go around because of the lagging phase shift. However, as the frequency increases to a large value, the phase shift is not going to be 180 degrees or minus 180 degrees, but it is going to be minus 270 degrees or plus 90 degrees, whichever way you want to look at it. And therefore, if I actually did an experiment, the polar plot that I will obtain will look more or less like this. Remember that this is not what you actually get. What you get are a number of points which we then are going to join by a smooth curve, and we really may not get very close to the origin, although we can try to apply as high a frequency as possible. However, we know from the fact that the number of poles is greater than the number of zeros that it is going to become very small anyway. So, this is what you will obtain experimentally. Now, this looks different from what we had looked at earlier because of this presence of this factor 1 by s. So, these were the curves that I had drawn earlier. Of course, this was for the case when the thing was in the upper half, but actually it is going to be in the lower half, as we have seen. So, this is what it is going to look like. Now, this is not the whole of the image contour gamma prime. So, I have to complete it by taking its mirror image. So, let me draw this dashed line to indicate the mirror image. So, this is one part of it, this is the other part of it, and this is corresponding to that semicircle business, a point which is very close to the origin, or the part of that curve is very close to the origin. So, I can essentially show it as going through the origin. So, this is going to be the polar plot, or the entire Nyquist image of the Nyquist contour. This is going to be gamma prime. Now, remember, I have to put arrows, and I did not do it earlier. So, let me now put the arrow on the dash part also. So, this corresponds to the upper half of the j omega axis, frequency increasing from DC to a very high frequency. Then this blob here corresponds to the image of the semicircle, which is virtually the origin itself. Then I am coming to the lower half of the j omega axis. As the frequency is very high, I am here, and as the frequency is decreased to DC, I go this way. So, this is what is going to be the entire contour gamma prime. Now, this is for some particular value of k, remember. Now, what about the relationship of this contour with the point minus 1 plus j 0? Now, I do not really know what is the actual experimental data. So, for whatever k I have chosen, I do not know where the point minus 1 plus j 0 will be on this diagram. But let us assume for the purpose of illustration that the point was here, minus 1 plus j 0. So, for that particular experimental value of k, the point minus 1 plus j 0 happened to lie here. Then what is our conclusion? Now, first of all, let us look at the sense of the traverse. The sense of the traverse of the contour gamma prime is clockwise. The gamma contour was also traversed clockwise. So, the two senses agree. So, when I look at the number of encirclements, I should take a number for which I do not have to change the sign, that is, put negative sign. But what is the number of encirclements by this contour gamma prime of the point minus 1 plus j 0? It is 0. So, the number of encirclements is 0, that is equal to the number of characteristic polynomial roots minus the number of poles of GH in the right half plane, which is 0. So, the number of characteristic polynomial roots is equal to 0, or the system is stable for this value of k. But now, suppose I change the value of k, what is going to happen? Now, this is where one has to be very careful. Suppose I change the value of k so that it is, say, double the original. Now, this whole contour is going to be scaled, it is going to blow out into the complex plane by a factor of 2. As a result, this point here is going to move out, it is going to be scaled by a factor of 2. So, this point may move out all the way here, and therefore, this curve will now look more or less like this, and I am going to show it as a heavy figure here like this, and this will be the part here like this. And similarly, for the mirror image, the dashed curve will now be like this, and the remaining dashed curve will be like this. The S along the semicircle part still remains very close to the origin, because multiplication by 2 is not going to change it very much. So, now the image contour looks like this, and let me trace it. Starting at low frequencies, I go like this, high frequencies along the semicircle, then low frequencies along the lower part of the j omega axis, and back to here. Now, what is the number of encirclements of the point minus 1 plus j 0 by the image contour gamma prime? It is no longer 0, it is 2. By drawing a radius vector from this and by looking at the intersections also, you can see that the number of encirclements is going to be 2 in the same sense, therefore, it is going to be plus 2. Let me trace it again, going here like this, then going like this, and then coming back. The total number of encirclements of this point is 2. Therefore, 2 is equal to the number of characteristic plane roots in the right half plane minus the number of poles of GH in the right half plane, that of course has not changed, which is 0, and therefore, the number of characteristic plane roots in the right half plane is now 2 and not 0. In other words, the system will now have become unstable. So, for this new value of the gain k, the system is going to become unstable, and we can see that if I increase the gain further, the system is going to remain unstable. Whereas, if I reduce the value of gain k from the original value, the system is going to remain stable for all smaller values of k. Now, this was exactly the conclusion that we had obtained by using the root locus method. That is, for values of k lying between 0 and some number, the system was going to be stable, but for values of k greater than that number, the system was going to be unstable. Therefore, the system was going to be what is called a conditionally stable system. This was the conclusion that we had drawn using the root locus method, and we can draw the same conclusion using the Nyquist criterion or the Nyquist method. And what about that critical value of k corresponding to the j omega axis intersection? That we can obtain from this also. If we know the location of this point, then what should be the value of the gain k, so that this point becomes minus 1 plus j 0. That will be the critical value of the gain, and that can be calculated.